Hi everyone, my name is Miss Hu, also known as Teacher Zian, and I'm a physics teacher. In this video, I am going to show you how to analyze the ticker tape that was obtained from a ticker timer experiment. So if you have no idea what a ticker timer is, then I highly recommend that you watch this video first, which is in the link above on the right. I'm sharing with you right now. So watch this video first because I explain what a ticker timer is and how it works and how you use it in the lab to study motion. This video is going to focus on how we're going to analyze the ticker tape, which is the result of this particular experiment. Now, let's take a closer look at the ticker tape before we start analyzing it. Along the ticker tape, you'll find that there are a lot of dots, and that's normal because the ticker timer has made all these dots. From the ticker tape, we can do a lot of analysis about the motion of the object that has pulled this ticker tape through the ticker timer. We can analyze the time taken, how far the object has traveled, that means the displacement of the object. We can also analyze the velocity as well as the acceleration. Now at the beginning of the motion, you'll always find that the dots are really close to one another, and that's normal because the velocity is 0 when it first starts moving and it's trying to get started, so the dots are all really near one another. And as the object moves down the ramp, you'll find that the spacing between the dots increases. And what this tells us is that the velocity of the object is increasing as it's moving down the ramp. Now this strip is quite long. Oops, and it's stuck somewhere there. Now, there are two ways to analyze a strip. You can analyze this single strip by itself, but I wouldn't recommend this unless the strip is really short. If you have a really long strip like this one, it is not recommended at all. If you have a really long strip, then I suggest you use the second method, which is to turn this long strip into a ticker tape graph. In this video, I'm going to go through both methods. Alright, so before we even start analyzing the ticker tape, first things first, we need to understand what the ticks are representing. I'm just going to move my face out of the way so that I can access this diagram here. Well, not diagram, I mean the shapes. So let's say, for example, this represents a ticker tape. And as we know, the ticker tape will have dots on them formed by the ticker timer. So I'm just going to draw some dots here randomly, just for explanation. Now, we know that the ticker timer has a frequency of 50 Hertz. I'm going to write frequency as F over here, 50 Hertz. What does 50 Hertz mean? 50 Hertz means 50 ticks in 1 second. Now, that means that the ticker timer is creating 50 ticks in 1 second. So 50 ticks in 1 second means that the ticker timer is creating 50 ticks in 1 second. Now, in a lot of books and texts, they always say that 1 tick is 1 dot. This causes a lot of confusion though, because when we start analyzing and then we'll start counting, we'll be very curious, like, wait a minute, there's 1, 2, 3, 4, 5, 6 dots here. But some books would say, oh, there's actually 5 ticks. So I've got students who've asked me before, how come there are 6 dots but 5 ticks? Now here's the thing. Even though we do loosely translate the meaning of 1 tick as 1 dot, it's not correct when it comes to analysis. So I want you to think of it this way. 1 tick actually is not 1 dot. 1 tick refers to the space between 2 dots. So it is the space between 2 dots. That means the tick is not this. This is 1 tick. Why? Because you see, if the ticker timer makes 50 ticks in 1 second, that means each tick will be 1 out of 50. Because 50 ticks in 1 second, that's a frequency. So if we want to calculate the period of 1 tick, that means the time taken for 1 tick. It will be calculated as 1 second divided by 50 ticks. That gives us 0.02 seconds. So each tick takes 0.02 seconds. So to make this a lot clearer to understand, you need to realize that the ticker timer doesn't take 0.02 seconds to make one dot. It takes 0.02 seconds to move from one dot to the next dot. That's why one tick refers to the space between two dots and not one dot itself. So 0.02 seconds to move from one dot to the next, and to the next, and to the next, so on and so forth. Now, to analyze this strip, we're going to ignore the first part where the dots are really close to one another because we can't see the space between the dots. That makes it impossible to analyze this section of the ticker tape. So we're going to ignore that, and that's fine because when we want to analyze motion, we want to analyze the entire motion and not just one tiny part. So we're going to take out the front part because that's not going to be important in the overall motion. We're going to start from the first visible space that makes it easy for us to calculate our motion. Now, although these dots are quite spaced out, they're still quite close to one another, which makes it quite difficult for me to demonstrate the first method to you. So instead, I'm going to take a later part of the strip, which is somewhere at the end. So you can see over here, even though the dots are quite close to the edges, the dots are still visible, and that makes it still possible for the calculation to take place. So we're going to use this part of the ticker tape for me to demonstrate the first method to you. So to explain the first method, I'm going to use a strip of 11 ticks. So I've got a piece here which I've already cut up exactly at the dot. So the dot's over here. We're going to count out 11 ticks. Remember that each tick is one space. So it's a space between the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what I'm going to do now is I'm going to cut this strip. Get off, scissors. All right, and this is the start. So I'm just going to indicate here start, and here's the end. Now you don't actually have to do this, but I'm going to stick this strip onto a piece of graph paper just so that it's easier for you to be able to see it on screen. Like I said, you don't have to do this. You can actually just analyze the strip as is. But I've got to do things to make it easier on video, right? So I'm just going to stick it in the center here to make it show up more clearly. All right, let's get started on the analysis. Okay, so what we have here is the photo of the actual strip which I have cut up and stuck onto this graph paper for analysis. So we're going to learn to analyze a single strip of ticker tape based on an actual result that was obtained from an actual ticker timer experiment. It so happened that I've cut the strip at exactly the starting and ending point. You don't actually have to, but I did, so just going to go with it. So we have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 dots, giving us 11 ticks. We can analyze the time, displacement, velocity, and acceleration of this strip. How to analyze the time taken? It's really simple because we know there are 11 ticks. We're going to write a number here so you can see. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 ticks. That means the time taken from beginning to end of this strip is 11 ticks times the time for each tick, which as we know is 0.02 seconds, giving us 0.22 seconds. As for the displacement, let me just change color just because. The displacement is quite simply equal to the length of the strip because think about it logically. If the trolley moves 10 centimeters, it would pull the ticker tape so that the ticker tape moves 10 centimeters as well. So how far the trolley has traveled is equal to the length of this ticker tape. Now, for this particular piece of graph paper, it so happens that each of these large squares is 1 centimeter from one line to the next. So this makes it really easy for us to calculate. So you can see over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and a little bit more, so it's about 14.2. So from here, let me just rub off all these numbers. Now, in your case, of course, just take a ruler. This would be a length of 14.2 centimeters in my case, giving me 14.2 centimeters in total. So if we want to calculate the average velocity, we just need to take the total displacement, which is 14.2 centimeters, and divide that by the total time, which is 0.22 seconds. And this gives us, I'm going to pull out my calculator here real quick, 14.2 divided by 0.22, that gives us an average of 64.545 centimeters per second. Now, is it possible to calculate the acceleration? Yes, provided that there is acceleration shown along the strip. So in this case, this particular strip, as you can see, the spacing between each of these ticks are quite consistent. So throughout this strip, the trolley is demonstrating kind of constant velocity. So we can't calculate acceleration in this case, because if you calculate acceleration, you're going to get a value of 0. So in order to learn to calculate acceleration, what I'm going to do is I am going to create a question so that there's something for you to be able to do. So I'm just going to create a ticker tape over here, and I'm going to create ticks. Okay. So now we have 1, 2, 3, 4, 5, 6, 7 dots, but there are 6 ticks. I'm just going to write this out to show you. We have 1, 2, 3, 4, 5, 6 ticks. So just like in the previous slide, if you wanted to calculate the total time, you just need to take it as 6 ticks times each tick, the period of each tick, which is 0.02, giving us 0.12 seconds. But that's not going to be our focus right now. We don't want to calculate time or displacement or velocity. We want to learn to calculate acceleration. So let us say, for example, this question gives us a value of 0.1 centimeter for the first part, and this part is, say, 0.5 centimeters, and this is the start of the tape, and this is the end of the tape. So in order to calculate acceleration, here's what you're going to do. You need to treat each tick as if it's a block of motion on its own. So what I mean by that is we're going to take this first tick and calculate the velocity for only this first tick. So I'm going to write that here. This will be our where our calculation for u would be. So the initial velocity is based on the first tick only. Now, how we calculate velocity is displacement over time. So the displacement for the first tick only is 0.1 centimeters, and the time for one tick is 0.02 seconds. So 0.1 divided by 0.02 gives us 5 centimeters per second. We're going to do the same thing for the final tick, which is between the two last ticks on this strip, which means tick number 6 over here. So for this final velocity, we're going to focus only on tick number 6. So for tick number 6, the displacement is 0.5 centimeters and the time is 0.02 seconds. Working this out, we get 25 centimeters per second. How do we calculate acceleration? Well, acceleration is calculated based on the formula of v minus u over t. So the reason why we've calculated u and v is so that we can take the values that we've calculated here and put that into our acceleration. So v is 25 and u is 5. But time is not 0.12. That's why I rubbed off the blue color time calculation just now, because that would have just confused you. You see, let me just move my face out of the way. All right. You see, the time here refers to not the total time, but the time it takes for u to become v. the time it takes for U to become V. So because U is one section, it's this section, and V is also one section, this section. We cannot take it as, we cannot take time from here to here. You have to think of time from this block to this block. So how do we work out the time? Like, how do you count time from block to block? What you do is you take time from the middle of this block to the middle of this block. How do we do that? Take it from middle to middle to middle. So if the ticker timer takes 0.02 seconds to move from this dot to this dot, logically, it would also take 0.02 seconds from the middle of this block to the middle of this block. Correct? So to calculate the time, you take it from the center of this block to this center. That's 0.02 seconds. Another 0.02, another 0.02, another 0.02, and another 0.02. So we count the number of 0.02s here. That means the number of movements we have. We have 1, 2, 3, 4, 5. So this gives us 5 times 0.02. So that's the value that we put for time at the bottom here under this fraction. So that's 5 times 0.02. Okay, I used the wrong pen in that case, but as long as you can see, that's fine. So this gives us 20 over 0.1, 20 cm per second, actually, because that's velocity over 0.1 seconds. And this gives us an acceleration of 200 centimeters per second squared. And that's how we analyze the acceleration for a single strip of ticker tape. So as you can see, it's not difficult to calculate, but this kind of analysis works best when you have a short tape. You have a really long tape, then it's going to be a little bit difficult because you count so many jumps in this case. So if you have a longer strip, it's better to convert it into a graph, as shown in this next section of the video. So now that you've learned the first method, I'm sure it's quite obvious to you why it's not a suitable method to be analyzing the motion for such a long strip of ticker tape. So instead, we're going to convert this long strip into a ticker tape graph. What we're going to do is we're going to cut this entire tape into strips, where each strip is made up of 10 ticks. Now, just as we learned in the first method, remember that one tick is not one dot. One tick is the space between one dot because it takes 0.02 seconds to move from one dot to the next. So if we're going to cut this ticker tape into strips of 10 ticks, that means 10 spaces. Each strip will have 11 dots. We're going to skip the first part because the dots are pretty close to one another, which doesn't make the calculation very clear. Is it possible to skip this part? Yes. As long as we're using parts of the tape, it's fine. Because trust me, this strip is going to be too long to fit all onto one piece of graph paper as well. So we're not going to use the entire thing. Now, depending on how quickly the trolley moved down the ramp and how long the tape that you have obtained is, you could end up getting a lot of strips. Sometimes you can even get more than 10 strips. Some of my students have even gotten 20 strips before. So we're not going to use the entire tape because that becomes a really complicated calculation. We're going to limit ourselves to maybe just 6 strips of paper. So in my case, I'm going to start maybe about here. It's fine to just pick any one. So I'm just going to mark it with a pencil. And you can see that I've drawn the pencil mark directly on one of the dots. Now, what I'm going to do is I'm going to mark out where we're going to cut the strips. And each strip will have 10 ticks. Let's count the number of ticks. Remember that each tick is the space. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this will be strip number 1. I'm going to label here number 1 because in case the strips get mixed up, at least we'll know, which comes first and next and so on. So from here again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be strip number 2. So what we're going to do next is we're going to snip snip. So we're going to cut the tape at the marks where we have divided the strips. So now that we've cut up all the strips, you should be able to appreciate why we've labeled the numbers 1, 2, 3, 4, 5, 6 on them, because they're all mixed up right now, and if we hadn't labeled them, we would have no idea which one came first. Okay, so I've got 6 strips over here, but looking at it, they're really short. So what I'm going to do is I'm just going to add on more strips to make this analysis far more effective. So instead of 6 strips, I'm going to cut up to 11 strips this time. Why 11? I'll show you why. So starting from here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be number 7. Snip, snip. So now that we've cut them all up, I'm sure you can appreciate why we've labeled all the strips with the numbers accordingly, because they're all mixed up right now, and if you hadn't labeled them, you wouldn't know which one was number 1 or number 2. So that's why we labeled them before we cut them. So what are we going to do with these strips next? We're going to stick them on a piece of graph paper. So as you can see over here, I have a piece of graph paper, and we're going to stick the strips on the graph, not horizontally, but vertically in parallel. Now in my case, I'm going to start right from the origin at the bottom here, because my graph paper already has labels along the axes. Of course, we're still going to label the axes, but just want to make it easier for myself. So we're going to start number 1. Where is my number 1? Okay, here it is. So here's my number 1, and we're going to glue on the strip. So I'm going to show you. We're going to glue them . We're going to glue the strip in a vertical fashion like this. So this is number 1, and we're going to do the same thing for the rest of the strips. So as you can see, I've already got all my strips pasted horizontally in a parallel fashion, and the reason why we've done this is because, well, it looks like a bar chart right now, which makes it easy for us to analyze the trend of the motion of the trolley. So the label that we're going to put along the x-axis here is time, which will be in seconds, and over here, now depending on what normally the question should be, sometimes it could be displacement and sometimes it can be velocity. So in my case, I'm going to put here displacement because it will be easier for me to explain the analysis based on displacement time rather than velocity time. If we put velocity time, it's going to get a little bit complicated. So we're just going to stick to displacement for this video. Now, in terms of what should be written as the scale along the axes. So let's start with displacement, which is on our y-axis, because this is a lot easier to explain. Now, displacement here refers to the displacement of the object from its point of origin. So we're going to assume that this is the origin point. So if this is 0, that means when we measure displacement, the displacement along this strip is basically equal to the length of the strip. Because think about it logically, when the object moves 10 centimeters, it would pull the ticker tape 10 centimeters as well. So that's why it's easier to label this as displacement. So let's start with the displacement axis, which is on the y-axis. We don't have to measure the length of each strip individually. All we need to do is just mark the length along this axis. So for example, as you can see from my graph, each of these large squares already are marked out, and if we were to just measure, just going to use this end, you can see that each large box is exactly 1 centimeter. So we don't have to measure that. We're just going to label this straight away. Here, this is actually 1 centimeter. And then the next one would be 2 centimeters. Where's the next one? This is 3, 4, 5. Oops, did I skip something? Yes, I did. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and I think we can stop there because, well, my longest strip is only up to 12 centimeters. Now let's look at the time axis, which is on the x-axis. So each strip happens to be exactly the width of 1 centimeters, which makes it really convenient in sticking on a piece of graph paper just like this. Right? And remember that we've cut up the strips into strips of 10 ticks. If you recall, let me write over here, 1 tick is 0.02 seconds, which means that 10 ticks is 0.02 times 10, giving us 0.2 seconds. That means the time taken for each strip now is 0.2 seconds. So I'm going to write here 0.2. The next one is another 0.2, making this 0.4. Then this is 0.6, 0.8, 1.0, 1.2, 1.4, 1.6, 1.8, 2.0, and 2.2. And there we go. So this is the graph of displacement time using the ticker tape, which I have just cut up. And now for the analysis. So what we have here on this slide is a photo of the graph which I have put together, and I've put it on this Jamboard so that's easy for me to scribble. As you can see, each strip is getting longer in length, indicating that the trolley was moving faster, which shows some acceleration. So if you want to do basic analysis like time and displacement travel, I'm just going to move the graph over here. Basically, total time is the time taken from the beginning of the motion all the way to the end of the motion. That means the total time of the entire 11 strips, as you can see. And because we've already worked out the time, we can just take the time over here, which is 2.2 seconds. I realized that my time seems to have disappeared from the photo. I'm just going to add that over here, the time label, I mean. Okay, if we had to calculate the displacement, then what we need to do is total up each length of the strip. That means you need to calculate the length of strip number 1 plus strip number 2 plus strip number 3 plus strip number 4 and so on and so forth. So we can just refer to the length indicated on the axis over here for each of the strips. So I'm just going to write out the length of each of these strips. So first strip is 3 centimeters. Next one is about 3.6 and so on. And what we will do is we'll total up all these numbers. And this is the total displacement of these entire motion from the start to end of the 11 strips. If you had to calculate the average velocity, you need to take the total displacement, which is 76.8 centimeters, divided by the total time, which is 2.2 seconds. And that gives us an average of 34.91 centimeters per second. Now, what if we want to analyze the acceleration from this ticker tape graph? So I'm going to create another slide. Whoops. I'm going to take this graph and put it here. And what we need to do is we need to see whether there is acceleration. So you can see, of course, that the strips are increasing in length, indicating that the velocity is increasing. And of course, that's acceleration. But is it constant or is it non-constant acceleration? And how do we figure it out? So this is how. I'm just going to get this line. What we need to do is we need to try to connect the top of the middle of each of these strips and see if we're able to get a straight line right through. So from here, I'm going to try to draw a straight line. And as you can see, you can't really get a straight line through. In fact, it's a bit of a curve going up, indicating that it's a non-linear acceleration. If we take a closer look, you'll find that actually we can get a linear line through most of the strips. Not at the first strip or the last strip though. So in this case, then how do we calculate the acceleration? I'm going to keep this simple. I'm going to focus on the middle section where we've actually gotten a straight line. So I'm going to ignore the first strip and the final strip. So how do we calculate the acceleration in this case? Now to calculate the acceleration, it's pretty similar to method number 1. We need to get the initial and final velocity. So in this case, the initial velocity refers to the first strip, and the final velocity refers to the last strip. So I'm going to label this as U and this as V. Remember, I am ignoring the first and final strip because they are not part of this linear graph which we're calculating the acceleration of. So we're only going to calculate the acceleration of this section where we are able to get a linear graph for the constant acceleration calculated.
Now, my apologies for the sudden jarring edit over here. It's because in the earlier release of this video, I didn't realize that there was a mistake in one of my calculations. So I've made this edit to put the corrected numbers in. So I apologize if the editing is a little bit in and out, but I really wanted to give you the corrected values. So the initial velocity is based on the first strip of the motion. As you can see from the first strip, the length of the strip is 3.6 centimeters. Now, velocity is displacement over time. That means the displacement is that length, which is 3.6 centimeters. The time for that one strip is 0.2 seconds. So you'll get an answer of 18 centimeters per second. Now, for the final velocity, we will look at the final strip of the linear part of the ticker tape graph. And as you can see from the graph, the length of this strip is 10.6 centimeters. So that's the displacement for the final velocity. And the time is only 0.2 seconds. You take the time for that 10.6 centimeters length of the strip. And this gives us 53 centimeters per second. To calculate the acceleration, we'll use the A equals V minus U over T formula, and we'll substitute the values of V and U inside, which are 53 and 18 respectively. T is the time taken for the initial velocity to become the final velocity.
And remember, T is not the total time, it is the time taken for U to become V. That means the time for this block to reach this block. So if you had watched the first method, you'd understand that this should be the same as well. It is the time from the middle of this block to the middle of this next block. Now, there are two ways to count this. The easy way is to take it from the graph. So from the middle here, this is 0.3 because it's between 0.2 and 0.4. And over here, the middle here is between 1.8 and 2, which gives us 1.9. That means the time is 1.9 minus 0.3, which gives us 1.6. Now, another way to get the time, instead of taking it from the axis, is to do jumps like, well, not you do jumps, but to jump from middle to middle like what we did in method 1. That means from the middle of here to the middle of here. This is 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 movements from middle to middle. And we know that each strip is 0.2 seconds. That means the total time from the middle of this strip to the middle of this strip is 8 times 0.2, which gives us 1.6 seconds, exactly as what we've calculated over here. So whether you use this method of obtaining it from the time axis or to jump from middle to middle like this really depends on what information is given in the graph, because some graphs don't have the time written on the axis at the bottom here, so you may end up having to jump from, from strip to strip just like this.
And the answer we get in the end is 21.88 centimeters per second squared. And that's how we calculate the acceleration for this ticker tape graph. And that is the corrected value for this graph.
So just to make this a little bit clearer, what if we don't use an actual ticker tape, but we have to answer questions instead? So I'm just going to create a question here so that we are able to answer the question. So I'm just going to create strips like this. Say we have 1, now let's say we have a question like this, and it's given that this is a constant acceleration motion. So if you check, oh yeah, it is constant acceleration because you kind of get a straight line that goes through the middle of all the tops of the graphs. I know it's not perfect, but I just drew this out, so bear with me. So I'm just going to rub this off because this is not necessary. And imagine that each of these strips already has 10 ticks. So we're going to follow the time that's written on the time axis. So if you had to calculate the acceleration, what you would do is the exact same thing like we did just now. That means you need to calculate the initial velocity based on the first strip. I'm just going to write it as U. And remember that you only take the values for the first strip only. The displacement of the first strip is 6 centimeters and the time is 0.2 seconds. So this gives us 30 centimeters per second. For the final strip, which is this one, we take the displacement of the final strip only, that's 18 centimeters, and the time is not 1.2. Remember, it's for this strip only, so that's between 1.0 and 1.2. That means it's also only 0.2 seconds. Just realized I didn't write seconds here. So 18 divided by 0.2 gives us 90 centimeters per second. So to calculate acceleration, we're going to use the formula v minus u over t. So we have 90 minus 30, and the time, remember that there are two ways to calculate this. You can take it from the middle here, so this is 0.1 to 1.1, so that's 1.1 minus 1.0. So time would be, oops, that's not straight. Let's try that again. So the time here would be 1.0 seconds. Or you can take it from middle to middle. So we can count from middle to middle here. So it's 1, 2, 3, 4, 5. That's 5 jumps. 5 times each strip is 0.2. And that's how you get 1.0. So this would be 1.0. So this is why we find that it's always 6 strips or 11 strips or some weird number like that, because then the time becomes a lot easier for us to calculate. So anyway, this gives us 90 minus 30, that's 60, divided by 1, 60 centimeters per second squared is the acceleration of this particular graph. So I hope you found this video educational and helpful in figuring out how to analyze a ticker tape, whether we're using the graph method like this or if we are analyzing a single strip of ticker tape. If you like this video, hit like and subscribe for more educational videos just like this, where I do my best to simplify physics for you to understand. Thanks for watching and happy doing experiments.